Welcome back, guys. In the previous lecture, we introduced the global variables, and today we'll start talking about blocks, that is group of expressions, which also will create local scope. Right, so here's our program from the previous lecture, and as you can see, we have multiple expressions. Right, we have the variable declaration, then the block with the nested variable, and once the block is finished, we'll need to see again the global variable. Okay, sounds good. So let's start from the block itself, right, the list of expressions. Right, the result of the block is the evaluation of the last expression. Okay, so we go through the list of expressions in a loop and generating code for each of them. And again, the last expression evaluated is the result of the block. Plain simple. And we treat the whole script, that is the whole program, as an implicit block, right? So it looks like this. And actually we can update the line when we do the parsing and implicitly wrap the whole program in the begin. Right? Don't forget to do this, since we handle the only expression, that is the top level block, is the program. And that should be it. Okay, let's try executing. And as you can see, multiple expressions are compiled. But take a look, we got actually an error. And that's because the inner variable declaration that is inside the block pretty much overrides the variable, the global variable. And this happens because we don't have yet local scope. Right, we just introduced the blocks to evaluate list of expressions, but currently block doesn't create an extra scope. And in today's lecture, we start talking about concept of environment. For those of you who have taken Essentials of Interpretation, should be familiar what it is. Just to remind, an environment is a storage of all the variables inside the scope, and the environments may also have a reference to the parent environment. Right, so, and this is how we get the environment chain. That is, nested scopes can access variables from the outer scopes. Now, LLVM has concept of the symbol table for all the variables. However, to handle our semantics, that is the block scope, we'll be tracking separate environment. So let's start creating it. Right, environment.h. Okay, so we represent environment as the class. And as we said, the main components of the environment is the record, that is the actual storage. And this is the map from the variable name to its value. And also a link to a parent environment. And since multiple environments can share the same parent environment, we use shared pointers here. Right, for example, 3 blocks may share the same global environment as the parent. And now let's introduce API methods for the environment. First of all, we should be able to define a variable in the scope, in the environment. So we use the define method, which accepts the variable name and its value. And pretty much to define a variable, we just install its value into the record by the variable name. Sounds good. To access the variable, let's use the lookup method, which will search a variable in the whole environment chain, right? Not only in our local environment frame, but considering the parent link. And to consider that scope chain resolution, that is the environment lookup, we use the method called resolve, right? Which will traverse the environment chain. And once we resolve, we can access record and get the value by the name. And of course, define and lookup should not be private, they should be public. And now let's implement the resolve method, which again should return an environment where this actual variable is found. Now, first of all, if our own record contains this variable, we just immediately return our environment. However, since we're shared pointers, we have to use, instead of this, share it from this. Right, for this, our environment class should extend the standard enable shared from this of type environment, and this will allow return shared pointers. However, if our record doesn't contain this variable name, we may still find it in the parent scope, right, in the parent environments. So we have to continue the traversal lookup. And the first thing we check if the parent is null, that is, we are in the very top global environment, which doesn't have any parent, we should throw an exception. Variable is not defined. Now for this, let's introduce the convenient macro called die, which will exit the program with message name. And let's quickly add this helper class. Let's call it logger h, which we can use for different types of logging, including error logger. And we want to use a streaming operator, so we extend the basic output stream and define the destructor for this class, pretty much showing the error message and exit the program. And our macro with the specific name die just creates an instance of this class. And once this instance goes out of scope, the destructor is called, so we will see the error message and exit the program. Okay, let's get back to environment. If parent is null, that is, we reach the final link in the environment chain and still didn't find the variable, we just exit the program. Sounds good? And otherwise, we call recursively resolve on the parent environment. Okay, so that should be it for now. Let's get back to our compiler. And also each programming language has so-called global environment. That is the pre-installed global object which contains all the global functions, global variables. So let's call from our constructor setup global environment, right, the helper method which we'll introduce. Let's include our environment class, right, environment.h. And let's store the global environment on our compiler, also shared pointer, and have the helper method to set up the values in this global environment. And for convenience, let's have the global object, which is the map from the string to value, where we can set all the global variables. For example, let's put here our version with the value 42, and then we have to create a global environment record, which is also a map from the variable name to a value, but we'll be calling the create global variable, the function which will also install all the information to the LLVM symbol table. So we go through the global object and fill the global record. Notice we cast the value to the constant because the initializer for the global variables should be constant. And so then we create the global environment. Notice again the parent link is set to null pointer. And going forward, our gen function should now accept the environment, right? Because to find variables we have to look up in that environment. And we always start our code generation in the global environment. So we have to pass the global environment. First of all, to function creation. Right, the functions are also symbols, so we have to install those symbols into the environment. We create the main function in the global environment, so we pass it here. And for convenience, let's define the type called env, which is just the shared pointer of environment. This will be easier to accept this as parameters. Okay, sounds good. Let's update our create function to accept environment and just use our define method to install functions. Now let's get back to variable access and handle generically the values. Right, currently, as you can see, we use just get initializer on the global variable, but as we said, the variable can be updated, so we cannot really use the initializer. What we have to do is we need to load the variable into a local variable. And we will start talking about local variables in the next lecture and concept of the stack and how we load values on the stack. And today just briefly talk about load instruction, which again takes the value of the global variable and loads it on the stack. So let's extract the variable name. And then to get the value, we just use the lookup method on the environment, passing the variable name, which again might be any value. Right, eventually it might be a local variable or a function, or it might be a global variable. Now to do this, we use dynamic casting from LLVM. So if we determine that this value is a global variable, we now have to load this value onto the stack. And for that, we use the create load instruction. Passing the type, right, and the type we can get from the initializer. Even if the variable is updated, the type should match. Passing the global variable itself and also the name. Okay, let's not forget to accept environment in our gen function. Also, let's update all the gen calls. Passing the environment here and also inside the block. Now, currently we will still have the problem when the local variable overrides the variable with the same name from the global scope. Now, this is because we don't create yet a local environment for blocks. For this, I'm leaving to do for the next lecture. And for now, let's just pass the environment. Okay, we updated all the calls. And from the main compiler function, we pass the global environment. That is our starting point. Okay, so that should be it. Let's try testing it. For now, let's comment out all the local variables. Again, we'll get back to next lecture. And let's check whether our version variable was installed in the global environment and whether we can resolve it. Let's execute. And there we go. We can see the global variable version is defined. But if we take a look at the variable access, we see not the ampersand prefix, which would be the global variable, but the percent prefix, which is the local variable. In this case, it's so-called register local variable. But as you can see, to get value of the global variable, we actually load it to the local variable with the same name. And this is exactly what the create load instruction did. It took the pointer to the global variable and loaded to the local version. And it might look obsolete from the compiler perspective, but this is exactly how the load store architecture is implemented. And the optimizing compiler is smart enough to optimize all these cases, for example, not to load global variable here. For now, we just need to understand the semantics. Okay, in the next lecture, we'll continue working with the local variables. Right, we'll introduce the local block scope, and we'll start talking about load and store architecture. That's it for today. Thanks and see you in the class.